I will be presenting our recent developments which we did in collaboration with Professor Tony and the group from University of Colloidal. And I would like to just say that the contribution is basically from Dr. Tommy group from Relevance, because they were the main drivers and they were represented on behalf of this group. And we did this investigation in collaboration, they did this investigation in collaboration with my group. And we are supporting this from the point of view, which we'll see in a later presentation, next session. So the basic question was, we are confronted with a problem of inferring the relation between, or the effect of the fly ash chemistry on the strength and stiffness of the interfaces and the strength of fly ash cement systems. So I will be talking about the importance of interfacial chemistry on the strength of slowly reacting fly ash cement composites. So the problem is, we are asking the question, what is the effect of the fly ash chemistry on the interfacial cohesion and strength in the cementitious composite? And the way how we would like to address this is by basically running the fundamental physics simulations coming from the molecular scale, atomic scale to the molecular scale, mesoscale and macroscale. So we'll be spanning across various time scales and various length scales. And what you see in this presentation, you won't see anything related to the testing of the concrete in compression, in flexure. No, we are purely doing this on a fundamental physics basis, in which we are using the models previously developed by the Krakowiak group and in collaboration with me, which basically are able to infer what is the structure of CSH, how the CSH will be interacting with certain surfaces, and how those interactions will propagate to the mesoscale and up. So we will start from the atomistic scales of the CSH, which is the left right lower corner, left lower corner on your side, and we'll slowly move with certain description of the physical processes up to the continuum scale, which will be the scale of the concrete in which you've got cement, hydrated cement and fly ash inside. And why do we do it? Because we had one of the projects in which we were confronted with a fly ash which is not well reactive. So it was basically fly ash type F. And we know from the literature that when it comes to the early strength of those type of systems, they are not performing the best. However, in the long term, you are gaining the strength. So the question, okay, why do they do not perform so well at the early ages? And then later, the second question, as they start reacting slowly with time, what happens at the ITZ and interface that perhaps is responsible for the strength, and what happens to the texture around the fly ash particles when the reactivity process starts and progresses. So the question is, what about the chemistry of the fly ash, of those slowly reacting fly ashes, and how does those chemistries interact with the CSH and various surfaces? So what we did and what I will be talking about is basically we'll start from the molecular level. A couple of years back, we developed the molecular level of CSH models, in which we know exactly the position of the atoms, how the atoms interact, and how they assemble in the structure. We have the potential fields for those, and we are able to estimate pretty reliably the strength, stiffness of those type of solids. So then, we also develop, and we know from the experiments that as CSH precipitates in the structure of the cementitious space, they form globules, and they form colloidal systems. So those particles of 5 to 10 nanometers size, which we know from the work of Professor Jennings, they coagulate and they create a matrix and they create a gel with a gel porosity. And there is a strong physical interaction between those. And of course, when you have now you've got cementitious material and then you've got fly ash, then of course there must be an interaction at the interface. There must be interaction of the interface between those CSH solids and between those fly ash particles. And these interactions will depend on stoichiometry of CSH, what the CSH is made of, in terms of the calcium to silicon ratio, the salinity degree, as well as the chemical composition of fly ash. And so we will be looking into using those informations that we developed in the past and tools to infer that what would be the effect of the CSH composition and composition of fly ash on the interaction at the interface, right in the first surface, and how does those interactions are strong, how do they propagate to some quantities like stiffness of your cementitious matrix with the fly ash particles. So where do we start? First, we were constrained by the project because it was all about low reactivity fly ashes, so fly ash type F, and we have two types of fly ash. which are pretty much similar, but in terms of the alkali's content and calcium content, there's quite substantial difference. So the hypothesis is that, and we now look at the macroscopic test from the company involved, that for those with the high alkali content, the strength goes a little bit higher. The question is why? Is it because of the interfaces? Is it because of the higher something else? So for this purpose, we've got those composition of fly ashes, which is measured with X-ray fluorescence. And then the question is, okay, let's use our tools to create a model of those fly ashes, how the atoms bond together and how the molecular structure of those fly ashes would look like. So what you see here on the left hand, you've got two molecular structures of fly ashes in which the skeleton is pretty much the same. It's silicon and aluminum, but what is different is about the concentration of those nice blue or cyan or green spheres, which are different cations. So one of them has a higher concentration of cations and alkalis, and another one has a lower concentration. And perhaps because of those differences, the interface properties or the interaction, how strong the interaction are between CSH and those types of two fly ashes, will be different. So having constructed those models of atomistic models, which we have the potentials for them, we know exactly how the atoms are interacting together. Now, what we are asking the following question. Since we have the structure of those fly ash at the nanoscale, molecular structure, since we know already the structure of CSH, so let's bring them close together apart. And let's see how they interact, how the potential field develops between those, and how strong those interactions are. So imagine you've got two flat surfaces, in which one flat surface is of a composition of fly ash, another flat surface is of a composition of CSH. And now we bring them closer and we measure the potential field. So what you see on those two, we considered two types of fly ash, two types of CSH stoichiometry. One, regular 1.7, which we know from the work is roughly 1.75 for regular CSH. And then 1.2, which is closer to the pozzolanic CSH, which would be created if you put pozzolanic materials in. So you have those red, blue, and green. Those are the potential wells for different type of the interfaces, the interactions. So the largest one, well, the red one, that's interaction between two CSH. Larger the well, stronger the interaction is. Great. So the two CSH, they like each other because there are strong ionic correlation forces and cohesive forces. That's why cementitious space, in terms of CSH matrix, is able to deliver so much of a strength and stiffness. But then, if you put the CSH, regardless if it's 1.1, 1.2, 1.7, in contact with the fly ash surface, then those curves are getting less shallow, more shallow. So we see the strength of interaction is decreasing. And then, but what we are observing that for fly ash 1, which is the green one, and fly ash 2, which is the blue one, which are different when it comes to concentration of cations, those two, they have low and different energy wells. So it means that the presence of cations and the concentration of cations in those fly ashes has an effect of how strongly CSH interacts. Larger the concentration of cations and alkalis, apparently our calculations show that the stronger interactions become. Less concentration you've got of those elements, lower interactions are. So there is a first kind of idea that perhaps this will be responsible for the lower compressive strength at the early ages, and for the relation with the chemistry. So now, for all, if you see those curves, those are basically free energy curves. So if you look at the first and second derivatives, you can estimate, okay, what is the stiffness of this type of a connection, what is the joint pressure, which is the force per area, and what is the interfacial energy. And every time when you look, regardless if it's calcium silicon ratio 1.2, 1.2, the indication is that, okay, CSH to CSH is the strongest, and that's intuitive. But then for the fly ashes, the one that has larger concentration of ions, cations, and sodium potassium ions appears to have a stronger interaction with the CSH. Okay, so if you would like to think improving the interfacial properties, aim at the fly ash in larger concentration of alkalis and cations you will have. At the same time, you also see that the pozzolanic CSH with lower calcium to silicon ratio is not as effective when it comes to strength, that 1.7 comparing to the disjoining pressure and to interfacial energy and bonding. So it's always CSH is the strongest. And one more thing what we did also we wanted to have a benchmark because we wanted to see what's the interaction, how strong the interaction will be if, for instance, you have only quartz. Imagine fly ash without any cations. It's basically SiO2 eventually mixed with Al2O3. So, but in this case, we just put SiO2, so simple quartz surface, to have as a benchmark. And it shows us that in those cases, the stiffness and the interfacial energy and the joining pressure, which is the force divided by the area between the two surfaces, are the lowest. So now we have the description of what happens at the interface at the nanoscale. We know if we put those two elements, A and B, together, depending what the stoichiometry is, we are able to describe the strength of the interface right at the nanoscale. So what do we do next? Because that would not be the part of the end of the story. So now we would like to know how collectively the CSA gel interacts with the fly ash particle. So we create what we call the mesoscale level, in which now the fly ash particle is a rigid particle. It's embedded in the medium of a colloid type made by CSH particles. Those CSH particles, they interact between each other, and we know how to describe those interactions. Now, fly ash has also its interaction with each neighboring of the CSH, because we already described this. But over there, we had flat-to-flat surface. Now the fly ash particle is a spherical object, and CSH also has a certain curvature and texture. So we need to account for those variations in the sizes, curvature, and texture, local texture, and orientation of CSH. So we modify the potential. Actually, Dr. Komi modified potential with the students. And we are able to account for the size effect and the curvature and texture into interaction. That's what you see on the right lower corner. And we also, of course, need to generate the colloidal structure of CSH gel, and that will be generated using basically Monte Carlo simulations and imitating all our CSH particles as spheres. The problem is quite complicated, so we are aiming to simplify as much possible in the reasonable framework. So if you decide to put as ellipses or this, that becomes a little bit more complicated at the upper level. And of course, we would like to be computationally efficient. So we generate those structures of those spheres of various packing density at various sizes, because we know that this distribution is not single, it's not mono. And you, of course, for the single monocyte spheres, you are able only to get 74 maximum distribution, and you need to employ polynomial distributions as well. So once we generate those structures, we need to validate that the CSA gel, this actually nice collection of the spheres, is actually performing in the mechanical sense as a CSA gel. If you are able to show it, it means that the interactions that you get between the particles and all your assumptions are correct. How do we do? For this purpose, we basically generate the hardness and indentation curves for our structures. We've got those different packings. We calculate, based on the interaction between the particles, the effective stiffness of this entire collective colloid and the effective strength of this entire colloid in terms of stress and tensile hardness. And we validate it against data. What type of data? At this scale, we have access to nano-indentation data. For those who are not familiar with nano-indentation, basically it's tiny tip, which is most commonly a three-sided pyramid, is pushed inside the colloidal structure of CSH, a solid of CSH, and then as you draw in and widen, you are measuring the unloading stiffness. Based on this and maximum force and contact area, you are able to predict the hardness. So what you find out that, as we expected, our potential and our assumptions and methods that we employ are able to reproduce the trend which we observed in the nano-indentation experiments from various groups, including our original group from which we came, from MIT, from Professor Hong. So basically, we have the packing for high packing density, we are pretty good. However, understand our data are not going less than 50% packing density because of the assumption of the interpretation of the data. But our collective actions of our particles, our potential interactions are properly describing variation of the indentation modulus and hardness in the function of the packing fraction. Therefore, as we have validated, then we move forward to the upper scale. So what do we do at the upper scale? Since we know how collectively the particles work together as a colloid, since we know now how the particles are interacting with the surfaces of fly ash particles, CSH and fly ash particles, so now we would like to know basically what happens at the at the interface when all this collective colloidal gel interacts with the fly ash particle. For this purpose, we create a model in which you've got a rigid fly ash particle. In this rigid fly ash particles is embedded in the colloid medium those nice colorful spheres. And then what you do is subject this three-dimensional cube to the traction in all surrounding, in all directions. Once you do it, of course, there will be deformation displayed by the distance increasing between the particles, between CSH and CSH particles and the CSH particles and the surface of fly ash. So we calculate the viral stresses as the collect in the first layer, and then we calculate the average spacing between the particles and the fly ash, and we are following the force versus displacement curve or stress-strain curve. So somebody may ask, okay, why do you take only the first layer of the interacting particles with the CSH? We did study first, second, third, and the first order effects on the interfacial properties and deformations are actually coming from the first layer of the CSH particles interacting with the surface of fly ash. So now by doing that, we are able to basically display and open the force displacement diagram about this, what happens in this first layer of the CSH on average basis with the fly ash particles. And as you can see, every time when the larger concentration of cations or alkalis is involved, the strength of the interface is going higher and higher. That's again, okay, it's in line with the stiffness evolution. Whenever we had a higher concentration of alkalis and cations in the fly ash, our stiffness of our interface between those two was also increasing. So now we are able to describe what happens on a collective basis between the CSH colloid and the fly ash particles. So we move one level up. But still we are not yet there when it comes to something that we can measure by compressive strength. Because what we are looking here is how the CSH gel interacts with the single particle fly ash, but the concrete is a mixture of hydration product and the particles of fly ash and CSH matrix. So what do we do next? We need to go up. So for this reason, now we will refer to the methods of homogenization, in which our concrete is basically, in this case cement paste, is basically a continuum material in which you've got fly ash particles embedded in the hydrated CSH cement matrix. In between those, you've got interface. Interface that you know from the previous step, the law of the stress-strain diagram, right? And you can describe as with K1, K2, K3 slopes, and you can capture the softening entire branch. So then you need to provide certain estimates for how the CSH matrix behaves when it's cement hydration. So we assume the full hydration of cement. We are able to, from the stoichiometry, to calculate the amount of the phases. We know the mechanical properties of each of the phases. We can calculate homogenized L effective stiffness. We also know the interface properties from the previous steps. So going forward, we can basically use the modified Mori-Tanaka scheme to estimate how much of the compressive strength our concrete would take when we have those type of interface defined by K and FKS, those stiffnesses which are in this case, in our case, are the same, and how much the strength would be under uniaxial state of stress. By doing so, we are able to produce those predictions that first, as the volume fraction of the fly ash is increasing, the strength in every case is going down. But most importantly, what is for our opinion was that every time, regardless of the trend, there is one trend which shows you that as long as you increase the amount of the cations, the black one is for the fly ash too, so the strength is always higher than for the fly ash, which has similar backbone but has a lower concentration of cations and alkalis inside. Okay, so then the conclusion would be that based on all our observations and all our modeling strategy, whenever you are thinking about increasing the strength of the fly ash cement system with this type of fly ash type F, which is slowly reacting, then if you experience higher concentration of cations and alkalis, most likely, and all the results point to that you have a higher interfacial strength, higher stiffness of the interface, and this will be leading to the increased uniaxial compressive strength. So that's the main result. And we published this work in Cement and Concrete Research for those who are interested. But what I would like to, before I finish, what I like to emphasize that I was a part of this work, but entire contribution, and most of the contribution comes from Magdi, who is the postdoc of Dr. Komi, and Dr. Komi itself, and our collaborator from Mitsubishi Materials Corporation, because they were the engines of this work, and the innovation comes from there. I was supporting in one way from the experimental point of view. So thank you so much for your attention, and if there are any questions.